Good afternoon to Professor Edwin Ekwe, Dean, Faculty of Engineering, Dr. Festus Olotuje, Head of the Department of Civil and Environmental Engineering, Professor Emeritus Robin Davidson Honor, Department of Geography, Environment and Geomatics, University of Guelph in Canada, Mr. Kishan Kumar Singh, Head of the Multilateral Environmental Agreements at the Ministry of Planning and Development, Trinidad and Tobago, colleagues, students, ladies and gentlemen. I'm Charmaine O'Brien Delpesh, lecturer and coordinator of the Coastal Engineering and Management program in the Department of Civil and Environmental Engineering at the University of St. Augustine. And I'll be the moderator for this afternoon session. It is my esteemed pleasure to welcome all of you from Trinidad and Tobago, the region, and the wider world to our webinar on managing the effects of sea level rise on sandy coast. For some of us in the Caribbean, it is almost dinner time. And I have to thank you for sacrificing this part of your afternoon, your culinary event, in the life of Caribbean people to be present here. So thank you very much. This evening's proceedings would not be long, but sufficient enough to whet our appetite on the important subject of sea level rise. We will have a very brief format, such as we will have an opening speaker, Mr. Kishan Kumar Singh, for about 10 minutes. He'll be followed by our featured speaker, Professor Emeritus Robin Davidson Arnott, after which we'll open the floor for discussions, questions and answers. You can use the chat box to post any questions, and you can identify who your question should be addressed to. Well, you would probably ask, why did I have this webinar? Why did Coastal program have this webinar? Why is it so important? I'll go back to probably 40 years ago, when there was a boom within the Caribbean for the tourism sector. And most of the islands started to mine their beaches for aggregate, for the construction industry. This caused most of the beaches to be decimated. And some of the 40 years ago have never recovered from this activity. To alleviate the problem, the coastal community, the scientific community, such as myself, 40 years ago, came together through conferences, meetings, to educate and inform policymakers, managers, our students and our colleagues. And today I can say that most of this activity has been significantly, or if not, stopped altogether in most of the islands. Now, 40 years later, our beaches in small island developing states such as us in the Caribbean are very small in size, measuring from 20 to 60 meters in width, are being impacted by sea level rise, which is considered a very prominent and consequence of climate change. Studies have shown, for Trinidad and Tobago actually, that the effects of climate change are causing serious social and economic consequences. There have been reports show that sea level rise with coastal erosion has impacted our beaches, which are used for the tourism sector, fishing industry, and not least but not the turtle nesting. So we can't afford for our beaches to disappear, which is what some scientists are saying, that by the end of the 21st century, most of the beaches will disappear. So today, we hope to be able to answer that question. What we need is science to drive some of our answers. Are our beaches going to disappear? In the past, scientists have used Brun Rule, a model to look at the impact of sea level rise on sandy beaches. However, it has been discredited, used by some, discredited by others. Today, we are going to ask our esteemed Professor Emeritus to present his alternative, the RDA model. And he will today compare both the Brun RDA model and hopefully answer some of the questions. Are our beaches going to disappear? Is it not as serious as we think? So that is primarily the setting for today. We're going to also have Mr. Kishan Kumar Singh giving us a bit of background on climate change and sea level rise. He's going to give us hot off the press news information from IPCC on what is taking place. So he's going to give us a little synopsis on climate change within Trinidad and Tobago and is applied to the Caribbean. So that is probably our afternoon session in a nutshell. So now I would like to introduce our opening speaker, Mr. Kishan Kumar Singh. Mr. Kishan Kumar Singh attended Queen's Royal College and then University of West Indies, and he majored in chemistry and analytical biochemistry before pursuing an MPhil in chemistry. He has been the lead Trinidad and Tobago negotiator on climate change for the past 23 years. And actually that's where we worked together on climate change issues. We were part of the climate change committee for many years. Prior to that, we worked together at the Institute of Marine Affairs. So I've known Kishan for many years. So today he's going to give us his wealth of experience on climate change matters. So he's also head of the Multilateral Environmental Agreement in the Ministry of Planning and Development, and overall lead on coordinating climate action and international reporting on various multilateral environmental agreements. So with all this knowledge experience, I would like to open the floor for Mr. Kumar Singh to give us a synopsis on climate change and sea level rise. Mr. Kumar Singh.
Thank you very much, Charmaine. Let me just familiarize myself with the technology, get my presentation up and running, which is somewhere here.
Oh, Mr. Kumar Singh, you are behind you on the beach at this time in the afternoon, but it seems to have some structures there. What is happening there?
Yes, this actually is perhaps what will be the norm. Enjoy the beach while you have it, I think. And the sandy beaches is, according to some of the projections, will likely disappear permanently. And the structure to the right is what would probably obtain those rocks and riprap to prevent the erosion from from going forward. So enjoy the beach while you have it, I would say. I gave a talk this morning on impacts of climate change and to the media, and I was telling them, and I'll say it again in the presentation, but I was just giving you a bit of an anecdote, that beaches and coral reefs at the rate of warming are likely to be decimated, not too far in the future. And some of the stories we are hearing now about dinosaurs would be the same stories that we would be giving our great-grandchildren if we live that long, but certainly our children will be giving our great-grandchildren, their children and their grandchildren. And I imagine our great-grandchildren or our children's children marveling at these coral reefs that once existed in the past. The sad part of the story would be that we were responsible for getting rid of them. And denying our children's grandchildren the enjoyment of what we had. It's a sad reality, but it's what I think is inevitable if we do not attend to the climate emergency. And why we have the climate emergency is precisely what the Intergovernmental Panel on Climate Change, the IPCC, has been saying in its latest report that came out in August this year, August 9th actually, showing the effects of climate change and what is happening and why it's happening, and what is the cause. And that cause is that human influence based on on human activity, primarily the combustion of fossil fuels for energy, increasing the concentrations of greenhouse gases in the atmosphere, such as carbon dioxide, nitrous oxide, methane, and other man-made gases such as ozone depleting substances, which are also greenhouse gases, and so on, have caused rapid changes in the atmosphere, in the ocean, in the cryosphere, a warming of both the ocean and the atmosphere as a result of these increases in greenhouse gases. And what is more alarming is that the rate at which the warming is happening has been previously underestimated. And each of the last 4 decades has successfully been warmer than any decade that preceded it since the start of the Industrial Revolution in the 1850s. And these graphs taken from the report basically shows what has been happening since 1850 in terms of temperature rises. And you can see most of that warming has taken place in the last 25 years, much around the time when I started negotiating climate change. So I've been there seeing it and experiencing it. All of us in this generation, I think, would have seen those changes. We were actually, if you take a deep breath, if everyone takes a deep breath, you would be the first humans to inhale air that has in excess of 400 parts per million of carbon dioxide in it. No other human being before us would have breathed in that air. And we would be the first humans to do that, to experience that, but we would be also the last humans to be able to do something about it. So the message is clear. The rate of warming has been unprecedented in the past many thousands of years, arising out of primarily human-induced climate change. It is projected that these changes may be irreversible because of the delayed reaction of the atmosphere to emissions of carbon dioxide and other greenhouse gases, being about 5 or 6 decades. And it is more than that, the causes of climate change, particularly the rise in sea level, is expected to continue over this coming century. So governments, having recognized that, have come together in Paris in 2015 to adopt the Paris Agreement, and the objective is to limit the warming of the global warming to 1.5 degrees above pre-industrial times or pre-industrial levels. And the graphic on the left shows where we are at now. We are in 2020, and at the current rate of warming, the 1.5 degrees that we set ourselves in 2100 will be achieved in the next 7 years or 8 years. So by 2030, we would have already begun to see 1.5 degrees warming at the current rate of warming, if nothing is done for reducing or to reduce these emissions. The current policies in place project us to be at least 3.9 degrees Celsius warmer in 2100, at which point life would probably be very, very difficult, if possible at all. And the message is clear. If you go back 800,000 years ago, from derived data derived from Vostok ice cores, for example, where they drill down cores and they examine the trapped atmospheric bubbles, you will see when they reconstruct the temperatures before today, they were well below. And at the current rate of increase, it is alarming. And these are some of the global observations. The global surface temperature has already risen by 1.18 degrees. Sea level rose about 8 inches in the last century. And what is more alarming is that the rate of that increase in the last 2 decades was almost double that of the last century. And that is only projected to increase going forward. And the acidity of surface ocean waters has increased by about 30%, because when carbon dioxide dissolves, you get carbonic acid, and that will have impacts on coral reefs, which are natural barriers to storm surge, which prevents erosion of sandy beaches, and also provides sands and source material for these beaches. So the evidence is clear In terms of the Caribbean, bringing it closer to home, we have already seen mean surface temperatures in Caribbean increasing by about 1 degree Celsius, occurring at a rate of about 0.2 degrees Celsius per decade. And therefore, at that rate, 1.5 degrees will occur by 2030. Sea level rises are rising at about 3 millimeters per year, and that rate is also increasing. This was determined as far in almost 10 years ago in 2013 through the IPCC report. And the global mean sea level rise suggests an indicative range of 0.26 to 0.77 meters by 2100. If you look at 1.5 degrees of warming, and sea level rise at the equator will be higher than the global mean, and we are near the equator, so it means more for us in terms of the level of rise. But critically, as I said, 70 to 90% of coral reefs will die at 1.5 degrees of warming, and 99% of all coral reefs will die at 2 degrees of warming, virtually being decimated totally. In Trinidad and Tobago, some of the projections, we can see an increase of between 2.4 to 3.6 degrees by 2100, and a sea level rise of between 75 and 126 centimeters by 2100. These are from derived modeling, downscale modeling. And that, of course, would have many multiplier effects on various aspects of biophysical and socioeconomic well-being. Changes in water availability are projected to be less over time, which would impact on agricultural production, potable use, human health for sanitation and nutrition and so on. Increase of vector-borne diseases because of floods. It would impact on tourism as a package, because all of the various sectoral impacts will be multiplied, because tourism depends on various sectors such as agriculture, water, resources, coastal resources, human health, and so on and so forth. I just wanted to put in these slides to set the context for the rest of the evening, which gives a pictorial illustration of what sea level rise could mean for Trinidad going forward. And for the year 2030, at the current rate of sea level rise, this is where the flooded zones will be, because we already have tidally inundated zones in the marshes and the swamps and so on. And if you look at the current rate at 0.37 meters in the year 2050, these are the flood zones will increase going forward. Coupled with with storm surges associated with extreme events such as hurricanes and storms, which are also projected to be more intense and more frequent with a warming climate. This is the projected inundation for a Category 2 hurricane if this were to occur in the year 2030. And contrary to popular opinion, God is not a Trini, I'm afraid to bring that bad news for you. And also that we don't lie at the outside of the hurricane belt as it is defined, at the southern edge. So being hit by a storm as we have been and a hurricane as we have been is not remote. And with the current rate of warming and the projections for increased intensity, this is not an impossibility, but this is what will happen should a Category 2 hurricane hit Trinidad in the year 2030 with the rate of sea level rise at that time. Given the rate at which hurricanes are now intensifying, this is something that will be of some worry. In the year 2050, if a Category 2 hurricane were to hit, this is the level of inundation you would get from storm surge. And for a Category 5 hurricane in the year 2030, although it's less likely, but certainly possible, this is the level of inundation that would occur. You would see that it would impact on many towns and villages and coastal areas, including those that have sandy beaches. And this is the same Category 5 in the year 2050, thereby changing what Trinidad would probably look like going forward. So this would, it means that climate change will have different things, different impacts multiplied among sectors, with impact on lives, on livelihoods, on food security, and would give a challenge, of course, to socioeconomic development going forward. And again, to respond to these threats globally, because it's a global issue, the Paris Agreement was adopted, and countries pledged to reduce their emissions through what are called nationally determined contributions. And what has been pledged so far is still not enough. There is still an emissions gap. And so we've heard of the term the climate emergency, because a lot more has to be done. We have to reduce emissions by at least 40% more by 2030, and then strive to carbon neutrality by the middle of the century. That is, balancing emissions with sinks or sequestration. Trinidad and Tobago has played an important part in the international global policy framework, having chaired the negotiations of the Paris Agreement in 2013 to 2014, and we continue to play an active part in the negotiations. The NDCs, as they're called, are supposed to be cycled every 5 years, with each cycle representing an increased ambition for more reduction in emissions than the previous commitments going forward, to incrementally reach the trajectory. We have in Trinidad and Tobago been quite active locally in terms of some of the actions implementing the Paris Agreement and trying to look at climate change impacts, including the assessment of vulnerability in various sectors, including the coastal resources sector, if you want to call it a coastal resources sector. We have defined it operationally as the coastal zone, and also taken some measures to reduce emissions going forward through our own nationally determined contribution to reduce emissions in power generation, industry, and transportation. And we continue to advocate for small island states, the peril in which they find themselves and a particular vulnerability that they are exposed to for projected climate change. We will do that again at the upcoming Conference of the Parties in Glasgow, carded for November, also called COP26, which we hope will also result in more climate finance, new climate finance goal going beyond the $100 billion that have been pledged so far. And among other things, looking at issues related to loss and damage, where things would be permanently lost and damaged as a result of climate change, both for extreme weather events and slow onset events. And that includes sandy beaches, which is the topic of today's deliberations. And I think that's a good segue, Charmaine, to take it back to you to introduce the other speakers to bring us some messages along the scientific lines that you have proposed in this workshop. Thank you very much.
Thank you very much, Kishan, Kumar Singh. I'm at the beach here. Everybody can see I'm on my favorite beach, Las Cuevas Bay. Hello to my supervisor, Professor Art Brun, and to my special friend, Professor Judith Wolf, all the way in Europe. And I know it's very late in Europe right now. So thank you guys for participation in this webinar with us. Mr. Kumar Singh, I was quite happy on the beach. I see you on the beach. Now, when you said it's irreversible, I don't know what to do. I'm starting to panic. So I hope that our next feature speaker, Professor Emeritus Robin Davidson Arnott, has better news for us. Professor Emeritus Robert Davidson is a son of the soil. Most people in Trinidad and Tobago didn't know that he is a Trini to the bone. He grew up in Cascade, Port of Spain, Trinidad, and attended Queen's Royal College, just like our previous speaker. I don't know what it is this afternoon, but they seem to be dominating this area of climate change. He was awarded an additional Island Scholarship in Modern Studies based on A-level results in 1965. He taught geography and history at St. Mary's College for a year before going to the University of Toronto, where he completed a PhD in geography. Study was on nearshore bar dynamics on the east coast of Canada. In 1976, he was appointed assistant professor in the Department of Geography, University of Guelph, and made full professor in 1988. He retired in September 2009. And when you see him, you'll think he is not retired. He has probably another 20 years again. I don't know if it's the Trini genes or what. And is now continuing research as Professor Emeritus and doing quite a bit of work. In addition to work on beach and nearshore sedimentation, he has studied coastal salt marshes, erosion of cohesive coasts, particularly underwater erosion, beach dune interaction, and dynamics of coastal sand dunes. He has published extensively in books and reference journals, and his book, which most of you who are students in coastal engineering or geography knows, Introduction to Coastal Processes and Geomorphology. And that was published in 2010, and then the second edition in 2019. During his career at Guelph, he supervised 35 MSc and 6 PhD theses. Robin, as he's known, was a member of the team that put together the shoreline management policy and technical guidelines for the Ontario Great Lakes, and was seconded to the Ministry of National Resources full-time from 1992 to 1993. He also served on the International Joint Commission Great Lakes Water Levels Reference Study Phase 1 from 1987 to 1989, and Upper Great Lakes Study from 2008 to 2011. His work was recognized internationally by a 2-day session held in his honor at the annual meeting of the Association of American Geographers in Seattle in April 2011. In 2012, he was presented with the annual award for distinguished scholarly contributions by the Canadian Association of Geographers. In 2019, the International Association for Aeolian Research selected him for the Distinguished Career Award. What a distinguished guest we have this afternoon. And that is why I wanted to invite as much as my colleagues in geography, coastal engineering, management, and my students, both past and present. And I see most of them are here. Great. So we will now ask Professor Emeritus to give us some good news. He's going to present his model, compare it to Brun, which some of you students would know. So Professor, it's all yours. Take the floor. Give us some good news.
Right, well, thank you. So, I mean, this is really a great opportunity for me because it's a long time since I've given any kind of talk in Trinidad, and to have so many people here is really quite uplifting. And I hope I will bring some good news. Maybe it may be a little bit too optimistic, perhaps, from what we heard from Kishan, Kumar, Singh before this, but I'll try and give you the good parts of it anyway. So I'm going to, because I don't want to keep you from your meals too long, I'm going to go and start sharing my screen now, and let's see where that goes. Oops, I'm going to have to go back there, sorry. There we go, right. Let me go back and try that again. Right. Right, I think we're there now. Sorry about that. It's been a while. So this is going to focus on the physical processes that control the response of sandy beach systems to sea level rise. the outline of what I'm going to say is here, and I'm going to focus particularly on answering the question, what should we expect when we have sea level rise impact on the sandy beach systems? I'll go briefly over the Brun and RDA conceptual models and the new expanded model that we published very recently here. And then I will end up with looking at some complexities and a little bit on the management implications for the Caribbean. And I hope this is where we'll have some questions and discussion around these. And I have to say, I don't have all the answers, but I have at least, I think, a few that would be helpful. So we begin with the context, which is that sea level is rising. Presently, it's around 3 millimeters a year, and in the Caribbean, it's, I think, slightly less than that. But as we've seen, what we see today may not be what we see in 20 years' time. And on a worldwide basis, this has caused lots of concerns for the impact on natural systems, such as salt marshes and mangroves, coral reefs, and sandy beach systems. And of course, we're also concerned with the impact on human systems through some of the things that Kishan showed us in terms of impact of major storm events and flooding on where we live and where we work and so on. And as a result, there have been many dire warnings, not just in the newspapers and so on, but also in reputable scientific journals. So, what should we actually expect? And I think what I'm saying here is, when we look at these warnings, we have to look at what is the science behind our understanding of what will happen. So one of the key things I think for us to do, and at least in terms of the physical parts of it, is to look at how did coastal systems respond in the past. And of course, the best place to look at is what happened during the last million or so years during the Pleistocene, and particularly what happened at the end of the Pleistocene, when we had the maximum ice sheet extent about 25,000 years ago, and sea level was about 120 meters below what it is today. So between around 20,000 years ago and about 5,000 years ago, sea level rose roughly 120 meters. Certainly in the lower latitudes, away from the ice sheets, and for most areas, it's kind of stabilized around 5,000 years ago. It's not true in every place, because there are, of course, other factors involved in here, such as tectonic uplift or subsidence. So we can ask ourselves the question then, what happened to environments such as we see in Buku Reef and the Bonacord Lagoon, beginning 20,000 years ago, when sea level was 120 meters lower. So much of the concern that we see about the potential effect of sea level rise on mangroves and salt marshes and coral reef systems, a lot of the attention in the sea level or the coastal literature has focused on how can these environments keep up with the sea level rise. In other words, if we look at a salt marsh or a mangrove marsh, is there sufficient deposition of sediment and organic matter to allow those systems to rise at the same rate or faster than sea level rises? And when we look at the coral reefs, can the organisms fix enough calcium carbonate so that they will keep up with that? Should we expect that to be the case? And of course, yes. One of the things we know is that coral reefs rise to something around sea level, and mangroves and salt marshes increase their elevation as a result of deposition. But for those, they don't actually have to do that. You know, in the effect of the last sea level rise, most of those salt marshes and coral reefs and mangroves didn't keep up with the sea level. They simply transgressed with it, because, of course, salt marsh vegetation and mangroves can migrate quite happily. They have seeds and vegetative propagation, and so when sea level rises a meter, all those corals and all those mangroves simply colonize the new area that is underwater. So that's one thing that I think we have to keep in mind, is that we have to make sure that our coastline is resilient enough or is managed well enough to allow migration of the shoreline and migration of these environments to happen. Okay, so when we get to sandy coastlines, of course, they're not living things. They are abiotic components of the coastal scene. And one of those papers that produce this sort of dire warning is one that was published by Vuzdukas et al. In Nature Climate Change. So this is a pretty major journal in 2020. It concluded that if we look at shoreline dynamics, combined with the sort of recession that we would expect as a result of sea level rise, that this could produce near extinction of about half of the world's sandy beaches by the end of the 21st century. And in fact, I guess from what we've heard, it might happen sooner than that. So this paper was based on a study for the EU that was carried out by very reputable coastal scientists and engineers. And so is what they say right, or are they wrong? And I would say to you, the key question here is this predicted loss expected in light of what we understand about the dynamics of the nearshore beach and foredune systems on sandy beaches? And my answer to that would be that it isn't expected. And so about 5 or 6 months ago, I published a paper with my co-author, Bernie Bauer, on controls of the geomorphic response of beach dune systems to water level rise. It's published in Journal of Great Lakes Research because I'm involved in a special section there. But it really looks at both water level rise on any system, and particularly in this case at the marine systems. And the primary object of the paper was to demonstrate that we wouldn't expect this predicted loss of sandy beaches. So that prediction really comes about as a result of the use of the Brun model, which was published by a Danish-American coastal engineer in 1962. And his conceptual model suggested that when we have sea level rise, this results in a transgression of the shoreline by this distance there, and erosion of the beach and dune, beach and berm system here. But the key thing that the Brun model says is that sediment that is eroded from here has to be taken out into the nearshore, and the nearshore is built up as a result to a level that is equal in thickness to the elevation, the elevated sea level. And if you're doing this over, 300, 500 meter distance offshore, you have to erode a lot of sand from here and deposit it on this. Now, in the 20th century, from 1970 to 2000, most people never actually use this. They use a corollary of the Brun Rule, which is an equation that Brun used to predict that actual recession distance R. And you can use that without worrying about whether the sand goes offshore or not. That's basically a simple inundation type formula. It has a length and a so it's basically the slope of this profile out to the limit of wave action on the bottom, and it includes the height of the berm on the beach. So it's a slope, and so you can use the Brun rule without worrying about the Brun model. But in the last decade or two, people, of course, have been using simulation models. And when you're trying to simulate, to predict what's going to happen to the beach system, you have to, and you're using Brun, you then have to take into account this need to transfer all that sediment offshore. So Vuzdukas et al. Assumed that the Brun model was valid. And as a result, it's not surprising that their model produced very large losses of sediment. Okay, well, that's the bad news. And here's what Charmaine asked me to do and produce the good news. So back in 2005, I produced a simple conceptual model that took a look at an alternative vision, if you like, of what happens to sandy beach systems when sea level rises. And to make it very short and simple, what the assumption here is that when sea level rises, as it does here to this point, the whole nearshore and beach and dune system transgresses landward. And the sediment that is in that system moves landward synchronously with the movement of the shoreline. So what happens then is you preserve the sediment because the beaches and the nearshore and the dunes migrate with that rise. It means you have to accept that your shoreline is going to move landward, but you hope that the sandy beaches that you like to lie on and that at Maracas provide you with bacon shark and so on, they will still be there. This is, of course, just looking at the physical processes of sea level rise, and there are other things that we have to accept. So I'm going to describe here then a bit about how this new model works, and I won't spend very long on the paper itself. Goes into a lot of detail about the stratigraphic or the sedimentological reasons, evidence from the last the Holocene transgression to show that the assumption of migration of the beaches is correct. I'm going to, if you want to read it, that's probably, if you want a good read, that's the place to go for it. But I'm going to try to just pick on a few things to show how it actually works. So in this revised model, we're looking here at dividing this section, the nearshore and upper shore face, the beach, and the foredune. These are the three components of the model. And we assume here that within each of these, the profile is in dynamic equilibrium, so that we allow for small transfers of sediment in from the deeper water and small losses if sediment is moved landward of the dune or the beach area. And there are a number of assumptions in it. There are a couple of key ones. A key one here is that the rate of sediment movements within and between these three primary zones is much greater than sediment transfers outside of the prism. And particularly here, we're assuming that the sea level rise is less than about 10 millimeters a year or a meter a century. And we're also looking at it at a time scale of decades to a century. Again, not because the model can't operate over longer periods, but because when you get to the century or more in length, your whole coastal zone starts to, you have to allow for evolution of the coastal zone. And so that means you have to take into account what evolution has taken place. Okay, so I'm going to look at what's happening in terms of the dynamics of the two of these zones of interaction, the nearshore and beach interaction, and then at the interaction between the beach and the area landward, the dune system that is there. So here's one of the very early publications on this by Shepard in 1950, and he produced this very classic diagram that shows that he was working off California, that in the winter months in California, you get big storm events and they erode the beach and they transfer sediment offshore in the form of 1 or 2 bars. And then in the summer months when the waves go down a bit, that sediment, those lower waves bring the sediment onshore and they build up your berm. So we have a kind of oscillation between these two states, between the berm with no bars and then in the winter months, a very flat beach and bars offshore. There are a whole range of different things. You can have a range of different things. So in the Caribbean, most of the Caribbean, we don't have nearshore bars, but we have a plain profile offshore. So if you go to Maracas Beach and go, you see you have a very planar profile going offshore. But we do get this erosion of the berm during calm period, during storm events and build up in non-storm. this has been shown, a whole range of different models have been built for beginning with right and short in Australia, and these have been applied in a range of different places, including in the west coast of France. By the guy called Bruno Castel and his group who are working there, and they produce this particular model. The one good example of the way in which this response comes from work that they did in Western Europe, because the years 2013, the winter of 2013-14 was one where there were several really large storm events, extreme storm events there. And at the beach on the west coast of France, where Castel and his group are working, the beach volume dropped 150 cubic meters per meter along shore. So huge volumes of sand went offshore as a result of these 3 or 4 extreme events. But one of the things we can see is that as you monitor the beach situation afterwards, and that's what's shown here in the green, over the next 4 years, the beach, all that sediment, that 150,000 cubic meters per meter length of beach came back. And so if you were there then in 2019 or 2020, the beach looked exactly as it did in 2013. The dunes, and that's in this light gray here, take a little bit longer to come back. So they've only recovered about half their volume by 2019. But in fact, if we go there now in the last year or so, we'll see the dunes are back nearly to their same volume. So what we can conclude from examples like this all over the world is that change in beach and nearshore morphology occurs continuously, and that the range of this change is very, very much greater than the sea level rise, which is a few millimeters, because these are on the order of tens of centimeters to meters. So given that, we would expect that the beach and nearshore system is quite capable of moving sediment landward to keep up with, on an annual basis, a few millimeters of increase in sea level. So let's turn then and look at the other part of this, and that's the one where we're obviously often most interested in, and that's what's happening between the beach and the dune. So in the beach and nearshore, that changes, this transport of sediment is driven by waves and by currents in the water. And when we come onto the beach, we have a change, because now in addition to the waves bringing sediment on and offshore, we have wind operating. And that wind will operate to take sand from the beach system and move it inland. Sorry, let me go back there. So that we have to account for the transfer of sand from the beach onto the dune system and landward inland from that. So many of the beaches in places like Toco and Maracas and so on, they are very, very low dune systems, but sand can still move inland from there. So Brun model never accounted for any dunes, but the RDA model assumes some kind of sandy coast backed by a foredune, or at least some sandy areas landward of it. And the details of the interaction of the beach with the dune varies with a bunch of controls, including the vegetation type and density. And they're obviously quite different from, that vegetation is different from, say, this foredune in St. Kitts versus this one in Southern Australia. So what happens during major storms is that there is erosion of the foredune, and that happens in a matter of hours to 1 or 2 days. The beach is flattened, and the dune here is scarped or eroded, producing a cliff that can be as high as the dune itself. And the two shots there, one is from North Frigate Beach in St. Kitts, and this other one here is from Skalen in Denmark, where if Art Kroon is here, he will know this area very well. And what we look at here is that erosion of the dune system, or the area landward of the berm, produces this beach slope that is the slope of the storm beach. And the junction here between the storm beach and the scarp of the foredune marks the limit that storm has produced. So you can imagine that each time we have a big storm event, it cuts back this area here, And if we were to raise sea level by, shall we say, a few millimeters or a few centimeters since the last major storm, then this arrow would follow the same slope as the beach, and it would produce an erosion that is further into the dune here. So if we add that up, from major event to major event over 100 years, the whole dune will transgress. And what we have to assume then is what happens to the dune itself. So the storm events in the Caribbean may be associated with hurricanes, or there may be big groundswell events, as are very common in Trinidad. So what happens to the dune system when we've had that? Well, here's a couple of shots from the Greenwich Dunes, which is on Prince Edward Island, where we've been doing a lot of work. And this is the beach after a big storm event in December of 2010. We come here after the winter and look at it here, and it's scarped the dune, and we have a big cliff here. And we take a look at this then 7 years later, 6 years later, and you see that in that period of relative calm over those time, we have built a big sand ramp here, which reconnects the beach to the dune here. And so in the winter allows sand to go over the crest of the dune onto the landward slope. And in fact, because we have had very limited storm events, this whole thing has become revegetated. And that vegetation is now creeping out onto the beach, top of the beach to build a little embryo dune, all of which provides some protection for that. The work we did there, and I just put this in to show you, is that we not only measured what's happening on the beach and so on, but we measured the actual transfer of sand from the beach to the dune system here. And this is a couple of field experiments where we're measuring wind speed, beach surface moisture, and we're measuring using some laser sensors here, the transmission of sediment across the beach and up onto the dune here. So we understand both what's happening on the beach and the wave action during storms, but we also look at how sediment is carried landward by aeolian transport. I wanted to put in something here that shows a little bit of what's happening along shore at this place that we're working. We're working on a big spit here. The whole thing that we're looking at is about 4 kilometers long, and we're measuring profiles, monitoring profiles along the length of this beach. And we did this from 2010 until we finished in 2018, actually. In this area here, we have longshore sediment transport from left to right in this direction. And this whole area here has a negative sediment budget, which means that there's more sand going out of the beach system here than coming in. So this area is erosional because of that negative budget. And as we go around the corner here, we get into a portion system where now we begin to slow down the rate of transport. And so the amounts coming in equal the amount of sediment going out. And then as we get further down here, we actually have a surplus of sand. We go to a neutral or slightly positive system. So let's look at what happens to the dune profiles as we go from this area here where it's negative to this area here where it's neutral or positive. This is line 5, which is the erosional one, and the red line here then is the profile in 2002, and this black line here is the profile that measured in 2016. We have them annually, but I've only shown the key ones here. So in this area where the sediment budget of the beach is negative, we'll see that the profile, the junction between the beach and the dune migrates landward. In this case, it migrates about 10 or 12 meters. And at the same time, the dune profile increases in elevation. So we may be eroding the dune system here, but we're also transferring sand landward because we keep scarping the dune slope. So the dune, the crest has now moved landward about 8 or so meters, and it has grown a little higher in height. If you go to the next line, we're getting here now near to the point where it's neutral, And so if we look, we'll see that there's a small migration landward, but only a meter or two. And the dune crest has moved 1 or 2 meters landward. So this is much more nearly in equilibrium. And this third line here at line 8, we're now into where we have a positive sediment budget. And we see, if we look at the thing, that you can see things oscillating back and forth, but there's no net movement of the toe of the dune and no net movement of the crest of the dune. It is just going a little higher, and we've continued to move sand over that onto the lee slope of it. And I should say this is all happening in an area where we have about 3 millimeters a year of increase in sea level. So you can actually offset sea level rise if you have a positive sediment budget. So that's one good thing. Okay, let me summarize this then. So that when we look at beach dune interaction, we have something similar to what we see in the beach and the nearshore, and that is a system that can be in dynamic equilibrium. And so the profile adjustments are on the order of 1 meter to half a meter, and the annual sediment supply is maybe a cubic meter to 10 cubic meters a year. So these are order of magnitude differences compared to the effect of the sea level rise. And so we can expect also then that the dune system landward of the beach can also adjust to an increase in sea level, and that it will shift landward synchronously with sea level rise. So that's the basic conceptual model updated to 2021. Well, one of the things we have done is to say, because we understand now how the system is actually moving, we can now replace the Brun Rule, which everybody has used for like 60 or 70 years, with a new rule, which we have called Robin's Rule. It's as good a name as any, and I've enjoyed it for 70 something odd years. So, and the Robin's Rule it's very similar to the Brun Rule in that it's essentially the slope times the increment in sea level, and that will give you the distance of the transgression. But the key difference here is that the slope that we use is the slope of the beach after the major storm event. So it's that storm beach slope, and it only goes from the top of the beach to the low tide line. There is no nearshore involved in this. We don't have to, in fact, invoke the nearshore whatsoever in this thing. And the key thing is that the variation in the storm beach slope between beach systems worldwide is much smaller than it is if you're looking at the whole beach and nearshore system. So what it allows us to do is to say, well, what kind of recession distance, transgression distance should we expect on beaches, on sandy beach systems? And so if taken here in this, we have a storm beach slope. Well, most of them seem to vary between 1 in 15 and 1 in 40. So 1 meter vertically to 15 horizontally to 1 in 40. And what I've done here is to say, well, okay, if we assume an increase in sea level of 0.003 meters, so 3 millimeters a year for 100 years, so a century, that will produce a transgression distance of 4.5 meters. So we should expect the shoreline to migrate inland 4.5 meters over 100 years. If we go to a much more gentle storm beach slope, 1 in 40, same sea level rise 100 years, we have a recession distance of 12 meters. Again, that's not a very big distance. So it's not quite as dire as some of the models would show. We say, okay, well, let's sea level rise at 5 millimeters a year. And those numbers increase to 7.5 meters, and the extreme would be 20 meters. So for, as long as sea level rise is kept within a reasonable level, say 5 millimeters or less, maybe 10 millimeters if necessary, then the recession of the beaches will be relatively small, and it is something that good management should be able to accommodate. And of course, we're relying on Kishan to make sure that we get the carbon dioxide levels down enough to keep that rate at less than 0.005 if we can help it. Okay, so as I said in the paper, we spent a lot of time looking for evidence of onshore transfers of sediment synchronous with sea level rise in the Holocene. And we use data from North and South America, Western Europe, Southern Australia, and so on. And that's all detailed in the paper. But I wanted to show you, and this is not in the paper as such, some of the evidence from the area we've been working in the Gulf of St. Lawrence, because it's an interesting one. And this is the Gulf of St. Lawrence here with Nova Scotia, New Brunswick, Newfoundland, and so on. And all the way around here, we have these big barrier systems that are very similar to these systems, or they're part of the same group, that are all the way along the east coast of North America. So we've been working in Prince Edward Island, and their measurements show that sea level has been rising at about 0.3 meters a century, 3 millimeters a year, which is roughly what it is in the marine thing. But this has been happening. We can measure that in the tide gauge in Charlottetown in Prince Edward Island, and that's it. It's about 3.2 millimeters a year there. And Don Forbes and a group from the Canadian Geological Survey extended this backwards as well by looking at evidence from coring and so on, in peat, wood shells and so on, all the way back 6,000 years. And they show that in this part of the Gulf of St. Lawrence, sea level has been rising at roughly that same rate, 3 millimeters a year for 6,000 years. So if we look at what's happening offshore here, we should see something in the neighborhood of 10 to 20 meters accretion of sediment if Brun is right. And if Robin is right, then there shouldn't be any accretion out there. That sand should be migrating landward. So let's take a look at that. Well, if we look at the shoreline in the Gulf, these are those barrier systems, and all that sediment this is what we see today. And these barriers have migrated landward as sea level has risen. And they're migrating through the processes that we see, overwash, inlets, and so on. And this is the coast of Prince Edward Island here. Again, a series of barriers, lots of sand involved in that. What happens when we look offshore? And Forbes and them did a whole series of side scan sonar offshore of the beaches here. These are the barriers here. This is the one that I showed you the picture of in Greenwich Dunes, and all the way across here is barrier systems. But once we go offshore about a kilometer or so, what we see is that all this red and orange is exposed bedrock. It's actually what's called a ravinement surface. So the sand that was on here has been moved landward as the sea level has risen. And so that sand that we see in the systems here has all been dragged across here by wave action. And you can see now there's sand offshore. The blue is the sand here. That's that transition then from the nearshore sands into this ravinement surface. And if you look at many of the surfaces on the east coast of North America and the United States, that's what people see as well, these ravinement surfaces. Sometimes it's not in bedrock, it's in old Pleistocene sediments, but the ravinement, the erosion surface is there. So this is a good evidence then supporting the idea that the rise in sea level is accompanied by a transgression and a migration onshore of all that sediment. And where's it all going? Well, it's going across the barriers as overwash. It's going into the tidal inlets here as tidal deltas here and here. It's migrating onshore in blowouts on dunes, and it's migrating from the beach across the dune system into the lee slopes. Okay, so obviously the model is a conceptual model. It is a fairly simple one in its version, but we have to accept that there will be complexities, and the model actually will accommodate some of those. So the onshore transgression, onshore movement of sediment from the lower shore face, we can accommodate, and we can also accommodate some losses. But when you go into periods longer than about a century or two, what's happening out there becomes important. So some areas will not have very much sediment, and so this will be very small. In other areas, we may have lots of sediment, and so there will be a continuous supply to increase the volumes in this area. So we can look at then what happens in the shore face, and we can see here an example where there's a lot of sediment out in the lower shore face, and that sand can migrate as sea level rises. But where you have a very thin sediment base, then the amount supplied to the near shore and the beach will be smaller, and so we cannot rely on that as something to offset sea level rise. In the south coast of Australia, they have a lot of sediment there, and so in fact they may actually have progradation of beaches even though sea level is rising. I don't know enough about the Trinidad situation, but my suspicion is that we don't have that. And we also have to look at what's happening on the landward side, and this is where coastal management really comes in. I mean, if you have urbanization such as you see in places like Miami, you can't migrate your dune and your beach because it stops right there. If you have a natural beach with a gentle slope, then everything can migrate quite happily there. If your slope is steep, and this could be a dune field, or it could just be you know, the soils over bedrock, then the rate of migration will be slower because it'll be the things will pile up here. The dunes will pile up. And if it's a very flat surface, so if you have a big marsh, like say then a river swamp, then you could lose quite a lot of your sediment because it does have to account for the building up the beach surface to the level of the sea level rise. So on the east coast of Trinidad, you're going to have to hope that you have enough sand offshore that it will compensate for that loss. Okay, I'm going to come to an end here and just say a few things in a minute about the Caribbean context. But one of the things one of the reasons for producing this paper was because people are actually now producing lots of numerical modeling, and the engineers in particular, and this is, many of my friends are good friends are engineers, but they tend to like to use the models. The modeling of the impact of sea level rise on beaches require, you can't just go and use depth 3D or you know, some of the other ones like that. Two recent models are examples that Halin et al. This is a group from Belgium, and Macarel is actually an Australian, but he was working with a group in Plymouth, England, and they produced two models recently that you can use to predict what's going to happen on your beach. But unfortunately, both of these are still using the Brun conceptual model, and this is a couple of the results from Halin et al. This is volume in your sand dune, and this is years from now. And you can see that the volume in the sand dune goes down dramatically. Depends a little bit on which profiles they put in and so on, but on which you know, which sea level rise model, which sea level rise scenario they use. But all the beaches disappear very quickly. So this is another example of you know, a dire warning from them. And I think the key thing here is we have to look at what is the assumption underlying the model. And in this case, the assumption underlying the model is that the sand will have to be transported. So they use, you know, standard modeling for beach and dune systems. And then they add in this, they have to actually go in and add in the transfer of sand offshore to fulfill the Brun requirement. So if we use the updated RDA model, that wouldn't take place. Okay, so just a couple of slides here, maybe to say what happens in TNT. And of course, if we're just looking at the sea level rise, it will vary with where you are on the islands. And so in Trinidad, beaches like Maracas and Macarip on the north coast, they have their own wave climate, and they are subjected to big swell events and so on. But here, these are both headland bay beaches, and so the beach can migrate. It's protected by the headlands, and it can migrate landward in both cases. At least in the case of Maracas, the infrastructure isn't too large here, so you can see migrating. You can see moving everybody 5 or 10 or 20 meters landward. Of course, at Macarip, they have built some shore protection here, which is probably the worst thing they could have done. This needed to be built about 20 meters further back, because any kind of wave activity here, you get reflection off this vertical seawall, and the sand goes offshore. And you don't have a lot of sand here to begin with. It's a small pocket beach. So there are things you could do: move this back and maybe bring in some beach nourishment, and you'd have a beach that people could really use. On the East Coast, of course, we have very long sandy beaches, this central and southern part of that, in Mayaro and Manzanilla. And there are obviously issues where you've got a coastal road very close to this, so that this might have to be moved. But and as I said, one of the issues here will be what's happening in terms of the volume of sediments offshore. One of the things that we haven't talked about, and I don't know what's happening here, of course, is that the sea level rise assumption here is that it's due to global warming. But of course, in many areas, we can have issues that arise because of subsidence. And that's something that I know is happening at the southeast part of Trinidad. And we also have to accept that in some areas, there is coastal erosion. There's just because of a negative sediment budget, or because you have very weak, you don't have these strong headlands like we have here. You have cliff coasts that are in weak sediments, and so they will erode. And so those are things that any reasonable coastal management plan would have to take into account. Tobago is perhaps in some respects a little closer to some of the rest of the Caribbean, and that beaches become much more important for tourism. I mean, a lot of people go here, of course, from Trinidad for their beach experience, but part of Tobago's economy is based on some tourism coming from Europe and North America. And so the issue of sea level rise becomes important. And of course, there are differences because these beaches here at Store Bay and Pigeon Point are all supplied with carbonate sediments from Bucku Reef, and Bucku Reef has to survive in order to keep supplying the sand to this location. And at Store Bay, we have a different situation, because you've got this uplifted coral platform here that provides us with some cliffs, very hard cliffs at the back of Store Bay. So the impact of sea level rise, you don't have, the beach here cannot migrate landward as easily as it can at Pigeon Point. But there are other beaches in Tobago that are classic sandy beaches, Charlottesville, for example, and Englishman's Bay, which is kind of a picture postcard thing. And here we have a sandy beach protected by cliff coast headlands here, and nothing built on it here yet. There's a little shack here for a little restaurant here. But this beach can migrate inland quite happily. It's the slope is steep enough. You haven't got a big swamp behind it, so it can migrate landward. So if we come back here in 100 years, I would expect to see exactly this beach here. And so, if Charmaine wants to come and lime on a beach, she can find it right here. It'll just be moved landward a little bit. And that, of course, is making the assumption that that humans don't do something here. Because, of course, in much of the Caribbean, that is a far greater threat to beaches than is sea level rise, or at least an equal threat. And we can see that here in St. Kitts, which this is North Frigate Bay, which is one of the big tourist areas for, and a picture of it from the ground. And you can see what's happening is that in some places here we have natural beach. That's down at this end. But in other places we have hotels that have been built right close to the beach, and they built a seawall, and then they find the seawall isn't good enough, so they put armor stone in front of it. And all of this doesn't help because, of course, this beach now transgression of this beach comes to a halt. This is Antigua, I think it's Sandals or something. And in Cuba, they have mostly done a different thing. They've tended to build the hotels far enough back, but they don't believe in letting any sand dune vegetation grow. This is all people, and they wall-to-wall people, and so that you tend to lose a lot of sand away from there. So what we see in this kind of situation is that we get that coastal squeeze. That is the beach and the near shore and the coral and so on cannot migrate because they've got human infrastructure that prevents that. And so a lot of developing good coastal management plans to allow for transgression of the beach, whether it's from sea level rise or coastal erosion, has to be give enough room to accommodate that. Okay, so I'm going to end there. This is my take-home message. If you believe the RDA model, then we can expect that the sandy beach and dune systems will translate synchronously with sea level rise, at least over the next century, and will not be altered substantially. So I won't be around in 100 years, but maybe some of you will be, and hopefully you will be sitting on some of the beaches in Trinidad and Tobago. This transgression is going to be superimposed on all other factors, subsidence. I mean, in places like Miami and the South Coast, in places like Los Angeles, that's an important thing. Coastal erosion. Much of the problems that people have in the Middle Eastern, sorry, the eastern part of the US is natural coastal erosion due to a negative sediment budget. And in many cases, those are more important than the sea level rise, at least for the moment. And so it's just one of the sea level rise is an important control. It may be a major one, but in many sandy beach systems, it's just one of the controls, and those controls can be natural and human induced. Of course, and I come back to what our first speaker was telling you about, and that is that I'm saying this, hoping that this all will be kept at least in some reasonable limits. But there are other effects on sandy beach systems. Sea surface temperatures are an important factor affecting your wind and wave climate, storm frequency and intensity, coral reef productivity, and of course the acidity, increased acidification of the seas is an important part here, and the effect, for example, of sargassum. And I know this has been a factor in both Trinidad and in Tobago. This big loads of sargassum coming ashore, something that certainly I never remember for when I was young. So you should be able to, with good coastal management, assist in the adaptation and reducing the human impacts on that. But of course, it also relies on not only Trinidad and Tobago, but places like one of the worst places, of course, is in North America, and Canada produces, almost as much carbon dioxide per population as, in fact, more than the US. So we have to do our role up here as well. Okay, so that's it for me. Over to you, Charmaine.
Thank you very much, Robin. I'm smiling now, as you can see.
I gave you your beach to sit on, right?
Okay, we open the floor to questions, and we have already a few, so I will start. The first one, I think it's for Mr. Kishan Kumar Singh. are the records of data with regard to sea level records of islands of the Caribbean. I would be interested in this data as a researcher to do future prediction using soft computer methodologies. Mr.
You know, Kishan, I've used the data from the satellite data, the JSON and so on satellite data, and I've used it also for the Caribbean, and it shows, I think, the latest, and I haven't updated it since 2018, I think, but showed about roughly the same as the worldwide data. I think slightly smaller, about 0.28 millimeters per year. And I think that's a good measure. But the one good thing is that we will continue to have that, year by year update in the rate of sea level rise. I know everybody says it's increasing, but the satellite imagery, satellite data doesn't show that, and a lot of the updated indicators from harbors and so on, they have not indicated that as yet either. So for the moment, I think if we take a sea level rise of 3 or 5 millimeters a year, that probably does us for the next few decades anyway. I don't, even when the increase in sea level occurs, it won't increase as rapidly as the carbon dioxide is increasing. That's my take on it. So I'm probably more optimistic than you are, but I don't have to to persuade people to cut back on carbon dioxide emissions.
Mr. Kumar Singh?
Yeah.
Where can the student or somebody get this data?
Well, certainly the satellite data that Professor Robin alluded to is one source, but I know that there are also tidal gauges that have been deployed to give you ground truth data. I'm not sure how widespread that network is, throughout the Caribbean, but I know we have a few in Trinidad from which that real-time data can be had. So I guess maybe whoever asked can do some more research wherever he or she is seated to see if that is actually the case in that island. But certainly those data recorders have been deployed. And also there have been assistance from international agencies through the Climate Change Center, for example, to supply these meters. So it could very well be that there is data already available in that place. So maybe some more research and digging up can unearth that information.
Okay,
Yeah,
thank you.
If I could just, there is an international group that collects globally the tide gauge data from all over the world, and of course have strict regulations in terms of making sure that these tide gauges are in places where where there is no tectonic movement, so that you are, and you can use the satellite altimetry and GPS to correct for any of that. So that's easy to find.
Okay, we have a question here. I think it's for you, Robin. Acknowledge that the RDA model is a simple conceptual one, but it may be interesting to see how the model may change if multiply effects and impacts on global warming and climate change are taken into account. For example, how would the conceptual model respond to increasing wave energy arising from more frequent storm surge from extreme weather events, as well as a loss of coral protection due to increasing ocean acidity and sea surface temperatures in island systems?
Yeah, the model can handle all of that quite happily, because it's based on so increased wave energy. Well, in fact, increased wave energy probably will make very little difference, except that it may have an impact on the rates, for example, of longshore sediment transport. It may have an impact on the rates of erosion of cliff coasts. And we see that in Canada too, because the loss of sea ice, both in the Gulf of St. Lawrence and the Great Lakes and in the Arctic, results in faster rates of erosion. But for sandy beach systems that are in dynamic equilibrium, the RDA model will operate quite happily with that. You might have to adjust slightly the recession rate due to sea level, but I don't think so. It should stay exactly the same, because if the beach is in dynamic equilibrium, it's in dynamic equilibrium. And we know that a beach on the California coast or the Oregon coast of North America with very high wave energy is just as stable as a beach in at Store Bay, for example.
Okay, thank you.
And yeah.
Another question here. Is it fair to say that the Brun Rule was appropriate for its time when sea level rise was less of a concern? Whereas the Robin Rule is more applicable to the current significant levels of sea level rise?
No, actually, no. The Brun Rule was it was wrong when it was formulated, and one of the issues that I was very unhappy with, which is what prompted me to write the first paper in 2005, was that people were going out and measuring and predicting transgression distances, but that's not a way to test whether the assumptions of the model are correct, because the model says that sand has to be moved offshore and builds up exactly synchronously with the rise in sea level. And so people never tested, they never tried to say, are the assumptions of the Brun model correct? And that's why we spent a lot of time in this recent paper saying, well, where is this big stash of sediment offshore? And we cannot find it anywhere. It is not there. That sand never got transported offshore and built up. What we see in most places is that ravinement surface, or that erosion, transporting the sand onshore. And you can see that in all along the east coast of North America and the Gulf. I work with people from India. You can see it there in the Bay of Bengal. And we see it in both in the Great Lakes and in the Gulf of St. Lawrence. So the Brun model never was right, but it looks so neat, you know. It's something you would want to happen, you know. Sea level rises, and then we take the sand off, and the amount that gets deposited is exactly equal to the increase in sea level. I mean, that's a wonderful thing. That's the way we would hope nature works, but it doesn't work that way. So, you know, I think that Robin's rule, the RDA model, was appropriate in 1962, except that I wasn't around to do that, at least not working in Coastal.
Okay, another question is, do you think that Macquarie area could benefit from the nourishment and a small revetment in order to keep the wall?
Listen, I've been there, what, a couple of years, 2 or 3 years ago now. I remember Macquarie from before, when it used to have fewer things. But yes, if you want to have people using it, because it's a nice enclosed pocket beach, you're not likely to lose much sediment offshore, and it wouldn't take much. We're not talking about huge volumes, because beach nourishment, you know, only works where you've got a relatively stable system. On the east coast of the US, many of the places they nourish, you have to keep nourishing, you know, 50 or 100,000 cubic meters a year. That you don't need that here. And I think if you redesign the shore protection behind to sort of protect the infrastructure at a higher level and set back further, you could have a nice sandy beach system and have your facilities and so on away from that.
Okay. I was never in support of that wall. As you said, it's a pocket beach. And putting that wall there has restricted the whole movement of the beach. I'm not even too sure beach nourishment should be even contemplated, because they're offshore coral boulder heads. And so it's a natural system that should have been left alone. It may not have been the most sandy beach, but I think people still enjoy it. Thanks for this. some reassurance, but it does depend on some key assumptions, like sediment supply, and still leads to beach migration landwards. As pointed out, human intervention may be even more of a problem. How do we persuade policymakers, coastal managers, to not make harmful intervention, especially in light of scientific uncertainty?
Well, that's a big question. I mean, I've spent a lot of time in Ontario and on the East Coast working with managers, and persuading the managers is not too difficult. The problem is to produce your coastal management policy and implementation to do that. I did that. I worked for a number of years to do that for the Ontario Great Lakes shoreline, and that's several thousand kilometers of shoreline. It's not a trivial thing. And I worked also with people. So I worked with the National Park in Prince Edward Island, and the managers there have accepted this. They've adopted it. They have moved facilities. They have moved a whole road, and they are going to continue doing that. They accept that the whole shoreline is going to migrate. But in other places, you see, even in Ontario, we have a policy, but its implementation varies with who's in power politically. And it comes under threat because people buy property and they don't want you tell them you have to move your property back, but they don't want to do that. They want to put in a seawall or bring armor stone and put in a revetment, and the politicians cave into pressure because the people who are doing this are the people who have large homes and lots of money and lots of political influence. So the answer is I haven't yet found a way of persuading everybody, and certainly not many politicians, to do that. But I'm hoping that the younger people now will be able to do that. I have exhausted myself as far as that goes.
Well, we have Mr. Kishan Kumar Singh from the Ministry of Planning and Development. We also have people from the Coastal Protection Unit and the Environmental Authority. So Mr. Kishan, maybe you could shed some light on planning in Trinidad and Tobago, coastal planning especially.
Yeah, I wouldn't want to speak for the coastal planning people who are responsible for this by any means, but I think some generalizations can be made. One of the things that we have to work with is the fact that we live on a small island, and it has inherent challenging characteristics. First and foremost, limited land space. And everything has to take place within that limited land space. And for small islands in particular, most of the economic development takes place in the coastal zone. So you have transportation links like roads, schools, settlements, things like that, agriculture. And therefore, policy decisions are often driven by these socioeconomic considerations first and foremost, particularly the political decisions. And even sometimes the political decisions themselves override any well-reasoned information. So, for example, in efforts to boost tourism, we find that there are ambitions to build huge and massive hotels on the beach where you want the tourist to step out of his bed into the water, which will perhaps happen invariably and inevitably. But if you take Manzanilla, for example, the trade-off in terms of allowing beach migration landward has to be balanced with the impacts of saltwater intrusion on a huge biodiverse freshwater system, which is the river swamp. And then how do you manage that? Saving the beach on the one hand, fine, allowing the dynamic processes to take place, but then in the light of sea level rise, landward migration might cause saltwater intrusion, and with the decreasing precipitation and decreasing water supply, that hydrostatic head of the nervous swamp will likely recede, and therefore you have more and more saltwater intrusion, which will disrupt the biodiversity and the natural features of a freshwater swamp, one of the largest in the Caribbean, I might add. So the science policy interface is always something that has to be, is always a challenge, because while the science may say X, the same science that tries to safeguard biophysical systems and therefore make it available for socioeconomic well-being sometimes conflicts with the decisions that are intended to maintain and protect socioeconomic well-being. So it's not there's no simple linear kind of decision-making process where you have a cause and an effect and perhaps a linear mitigation measure that can work in every and each situation. So again, it's a bit tricky when it comes to that, particularly in small and developing states.
Yeah, agreed. Professor, are there any suggestions, recommendations how we here in Trinidad, we have a geography department at UWI in St. Augustine, one in Mona, Jamaica, how we can attempt to start using your RDA because it seems to be applicable. Maybe you could give us some guidance and you can challenge us to undertake some studies. I think we would like that.
Yeah, I mean, there are obviously, first of all, the RDA model is a conceptual model, and so you have to apply it to whatever management plans you have. There will be situations where you need to do modeling, and so if you're looking at in a particular area such as Manzanilla, what are the longshore sediment transport gradients and so on, and you might want to use the Delft 3D or something like that. There will be smaller models coming out now that look at specifically at Sandy Beach and Dune in 2 dimensions, so using X Beach and something else that looks at transfers by Aeolian. And one of the problems then is having the data that will feed these, and I understand that, but there are now a number of simple systems that allow you to collect data remotely, and I'm thinking here then of drones, which I know that people are using drones in Trinidad all over the place. I've seen videos of Mayaro and Manzanilla from drones, so that it's fairly simple to do that, and you can use structure from motion software to produce it. So you don't have to have really expensive instrumentation now, as we used to have to do. And the other thing I would say is that a lot of what's happening on the beaches you can tell now because we've got that historical data. So you can begin with the air photos from, I forget, is it 1958? I'd have to go back and check that are available, and then we have air photos, and now of course all kinds of satellite imagery and radar altimetry and so on. So that an important way of predicting what's going to happen in the future still seems to me to be looking at how the system has evolved over the last 3, 4, 5 decades, and using that as an indicator as to what's going to happen in the next 3 or 4 or 5 decades. That's still a really, really good way of doing it. And there's something obviously that changed. So you have to look at, okay, so this is what happened over the last 50 years. And these are a couple of the major things that may have changed now. So building structures, putting in piers, building a big hotel, what has is it Cocoa Reef Hotel done to Store Bay, that kind of thing. But you can evaluate that, and you can use the air photos and the on Google Earth and that sort of thing to produce really good studies of what has happened and therefore what predictions in the future.
Your model had dunes in them and show the importance of dunes. However, one of the things I find in Trinidad and Tobago, I don't think we've recognized, well, some people don't even know that we have dunes in Trinidad and Tobago. There's some in Las Cuevas, maybe, quite small in size. And then our favorite beach, Maracas, because it's a very windy beach. And I would say approximately 20 years ago, there were traps that captured the sand. And the plan was to create dunes, by putting vegetation and trapping the sand. And that was removed. So we are losing now the sand that would have been trapped and formed dunes. And I think it's being lost altogether because they ended up beyond the car park, beyond the road in Maracas. Maybe you can make some strong statements on the importance of dunes.
Well, yes. I mean, let me say first of all, and one of the things is that as we think more about the application of the model, you don't have to have a big sand dune for the RDA model to work. You do for the Brun model, but you have to have a big reserve of sand, otherwise everything disappears. But for the RDA model, it doesn't matter. For sand, for beaches with relatively narrow widths and small dunes, or virtually no dune at all, it doesn't matter. But yes, at places like Maracas, a concern would be that when sand is blown inland beyond the limit of wave action, that is lost until the beach itself transgresses that way. So what you can do then is that you saw for the profiles that I presented that we were getting in Prince Edward Island 1 to 3 cubic meters a year of sand per meter distance of beach into the dune. No, even when the beach budget was negative, you're still getting that transfer. And so a big part of developing a management plan is to produce this sediment budget for the beach and for the dune system. And we have to remember that when the wind blows sand onto the dune or inland, it's a loss to the beach. Now, in the natural system, the beach replenishes itself by then having a storm and bringing sand back onto the beach. But if the sand goes beyond the dune system, it's lost. And if you don't have a lot of sand, there's not a huge amount of sand coming into Maracas. The river doesn't bring that much, and there's a little bit of erosion. But my impression would be that you can't afford to lose too much sand inland, beyond the parking lot, as you put it. And that's true worldwide. That if you're used to having the sand trapped in dunes and you then remove those dunes, it goes. And that's why some of the beaches in Miami, that's an issue because the sand is being blown into streets. In the picture I showed of Cuba, that's another issue. They have removed a lot of their vegetation, it's lost. It's going into the area beyond, some of it into the mangrove lagoons behind. So yeah, so Maracas is one where restoring the vegetation and allowing dunes would be a good thing to do. And I work with people on a Great Lakes beaches. It's the same thing, persuading people that you can live with some plants landward, and put your beach. Those plants really work when there's a big storm and you're not on the beach. Then maybe a few hardy people doing some surfing in the water, but most of us aren't sitting on the beach in a big storm. So that's what the plants are there for, is to trap the sand, and then that sand can be brought back. And you may lose some of the front face of that vegetation, but all those dune plants are trained, as soon as they've eroded, they start moving, those runners go over the surface and they restore it. So that's how a natural beach would operate. And you could do that. And you just have to have, your car park far enough back and then some walkways that go across the dune to the beach.
Thank you. We have time for a few more questions. Any more questions from our attendees? No more questions? One question to Mr. Kumar Singh. Is all lost with respect to climate change, even though we reduce our emissions? Because you mentioned that. Is that a fact, or is just to scare people?
Well, no, it's a statement based on the scientific evidence. True, and I say that scientific evidence is gleaned from peer-reviewed publications. You were a member of the IPCC, so you know how it works at some point. So yes, it's a collection of the scientific data and information. in respect of climate change, various aspects of it, and making statements based on that. The thing is, and I just want to come back to the whole issue of equilibrium. The world will equilibrate and beaches will equilibrate wherever they end up. And we will end up in a state of dynamic equilibrium, regardless of what the disruptions are. The question is whether the extent of disruption will maintain the system as we know it and as we want it. I think that is a critical question that we want to address, because the world will exist with climate change. It has done so for millennia. This is not the first time that we are seeing climate change. It has happened over millions of years. The question now and the problem now is the rate at which it's happening. And it is happening at a rate that does not allow that equilibrium to happen over the time period that has happened in, in the past. And that is the reality that we have to face. And I want to come back to, I think, Judith's point about harmful interventions in the light of scientific uncertainty. And certainly, if we stick to the precautionary principle and erring on the side of caution, I think that is the way to go, because then you end up with a win-win situation in any event, because it would be measures worth doing in any event. You will not end up with a loss, you will end up with a gain. And if you don't end up with a gain, you will end up with maintaining the status quo, which will not be a loss. Measuring these interventions and these options against what the impacts are, it certainly takes into consideration, can we live with, would be allowed to live in the first place? Because with the current emissions rate and the climate projections, the global projections, we are in store for a 3-degree rise by the end of the century. We are in store for a 1.5-degree rise in 2030, which I'm sure all of us will be around for, at which point coral reefs will be 99% gone. And that would be from temperature increases and from ocean acidity. And of course, the world will re-equilibrate, but would we have sandy beaches left? I don't know. I think the jury is out on that, but certainly the projections are in.
One question here. What are your thoughts on the depth of closure? I think that is for Professor.
The depth of closure is something that's used quite a lot. Of course, it has been used in the application of the Brun Rule, because Brun had marked it as a point, transition from the nearshore to the offshore and so on. The depth of closure has been defined as a sort of limit at which we see a change in the elevation of the bed over an annual period. It's a useful point conceptually, but it's really hard to measure easily. And the other problem here is that it marks the boundary really between the upper shore face and the lower shore face, and we know that that depending a bit on your wave climate, that we can transport sand beyond that seaward, but also we can transport sand from seaward of the depth of closure into the near shore. And so that's why we allow in the new version of the model for sand to come in from the lower shore face, because it does in many places. And how much sand comes depend on, if you have big enough swell waves often enough, and it also depends on how much sand is out there and what the slope is and so on. But so the depth of closure is an interesting conception, but it to me it's not a critical point.
Okay. Thank you. Well, if there are no more questions, we've had very positive responses. People are complimenting the panelists. Very interesting and inspiring seminar. Very much enjoyed it. Informative presentation and very relevant discussion as relate to our local beaches. So it brings me to a close now to thank the panelists, both Professor Robin Davidson-Arnott, Son of the Soil, and Mr. Kishan Kumar Singh, with his 23 years experience in climate change, for a very informative discussion. For Robin on his model that I would throw a challenge to our students and teachers in geography. Hi. And for the coastal managers out there, who are present today, Professor has shown us that we have quite a few sandy systems that can migrate inland if they're allowed to. And it would be remiss of us if we don't allow that to happen. So all is not lost. So it's up to us as coastal scientists, managers, planners, to take the rein and actually manage our coastal systems. And I say that as I started out, when I said they were mining the beaches 40 years ago, and it may have been a slow progress, but we had meetings, conferences, we met with politicians, even in Tobago, when it started, we met with the THA, and it came to a stop. So there's no reason why we as scientists, managers, and planners can't do the same. It will be hard work, but I look forward to us working together. And that is one of the objectives of this conference, to bring the scientists together, planners and managers, right? To be able to manage our system. As Kishan said, we have some challenges ahead, but there's no reason why we can't work together for the betterment of both Trinidad and Tobago, the region, and the world. I would now hand over to the head of department, Dr. Festus Olatuje, to give the vote of thanks. Professor, Dr. Olatuje.
Thank you very much, Chairman. Good evening, everyone. I'm Professor Edwin Ekwe, the Dean, Faculty of Engineering, University of the West Indies in St. Augustine. Professor Emeritus, Robin Davidson Arnott, Department of Geography, Environment and Geomatics, University of Guelph in Canada. Mr. Kishan Singh, the head of multilateral environmental agreements at the Ministry of Planning and Development in Trinidad and Tobago, colleagues, students, distinguished ladies and gentlemen. As the saying goes, all good things must come to an end. And so, too, unfortunately, is this wonderful, informative webinar. And so, on behalf of the Department of Civil and Environmental Engineering, I have the pleasant duty to express our gratitude to all those who have directly and indirectly contributed to this lecture on managing the effects of sea level rise on sandy coasts, which has been organized by our Coastal Engineering and Management Program. At the outset, I thank our featured speaker, Professor Emeritus Robin Davidson Arnott, for allowing us to disturb his restful retirement to share with us his very insightful and informative presentations. Thank you very much, Professor, for contributing to the transfer of knowledge in this important area to our country and the wider world. Given the makeup of the listenership at today's webinar, we were really enlightened with your knowledge and very happy with your presence. Welcome back, sir. We also want to thank Mr. Kishan Kumar Singh for taking time out of his busy schedule to deliver the opening remarks. The webinar could not have asked for a better opening batsman. Well done, sir, and thank you very much. Special thanks to the staff of the Coastal Engineering and Management Program, Department of Civil and Environmental Engineering, and UE Marketing and Communications, for their unflinching support and coordination. Our heartfelt thanks to the coastal engineers, the scientists, the managers, geographers, professors, and lecturers, and students, both present and past, for your interest and active participation in this webinar. So therefore, with these warm words of appreciation and gratitude, we have now come to the end of today's webinar, which would not have been possible without all of you. Thank you, and good evening.
Thank you, Dr. Latouche, for those thank yous to all who've contributed to make this a success. I'm being challenged now to have another one. Okay, but that wouldn't happen in 2021. As we come to close, a lot of people have asked for the recording of this webinar. It will be posted on the civil engineering website, so you can get the full webinar if you weren't able to stay for the entire session, okay? So again, as we come to an end, not just physically, you can keep in contact. We have a list of all the participants, and I'm sure some of you would like to be in contact with Professor Robin Davids-Nanot, and also Mr. Kishan Kumar Singh, who has a wealth of knowledge on climate change and sea level rise. So, gentlemen, thank you for a pleasant afternoon. I thoroughly enjoyed it. It was my first host of a webinar by myself. So thank you. You're both from QRC, so that's a special. And I'm from the girls' school. I'm from St. Francis Girls College. So it's a special evening.
I think that Kishan was there a bit after me, though, you see, so.
Yeah, and Shamin, actually, St. Francis is our sister school.
Yeah.
So it's a bit of a.
I was there, yes. So that was quite coincidental. So thank you very much, Professor. We'll be in touch.
Okay,
and
thank
all
you.
the geographers too. They
And
will all be.
I would like to be in touch with Kishan as well, because I really enjoyed the presentation, and I think that I don't want to downplay the impact of climate change too much, because it's certainly an important thing, and I hope to keep diving on those coral reefs for a while longer.
we all of us.
Yes, right. Yeah.
Okay. Thank you.
Well, thank you. Good to see you. Thanks. Bye-bye then.
Thank you very much.
Have a good weekend. It's Republic Day tomorrow in Trinidad. Happy Republic Day, and a nice long weekend for everyone. So do enjoy the weekend.
You could have almost stayed on that beach, you know, Kishan, but I think it's
all
closed.
good things do come to an end.
Yeah, I noticed I was the only one who didn't have a beach, eh?
We had many beaches.
Okay.
So.
Yeah.
Thank you. Thanks
Okay.
to marketing
Bye-bye.
and communication.
Okay. Bye-bye.
Yeah. Bye.
And to Stan Green, thank you very much for a lovely afternoon. Bye.